as a okay, so let's get started. So this is more of an algorithmic talk, less of a statistical talk. So it's going to be a little different. Okay, so the motivation is policy gradient methods require recomputing the policy gradient at every iteration. Okay, so at every iteration, if you want to update your policy, you need to recompute the policy gradient. And these methods have theoretical guarantees, even with function approximation. Okay, so there are like these guarantees. But the problem is each interaction with the environment is expensive because you need to interact with the simulator that can be slow. So ideally, what we want is to update the policy many, many times by interacting with the simulator or the environment just once. Okay, and all of these kind of popular methods like TRPO, PPO, MPO, they rely on constructing surrogate functions and update the policy parameters to maximize these surrogates. So instead of directly trying to maximize like the value function, these try to maximize these surrogates. Okay, and they support off-policy updates. So in this talk, off-policy updates refer to that you can update the policy without requiring additional environment interactions. Okay, and they have like very good empirical performance used in deep RL. Everything is good, but there are theoretical guarantees only in the tabular setting, and now I think in the linear function approximation setting. But they can fail to converge in like some scenarios. So there's like this very nice paper by Xu et al., which constructs like these counterexamples for like PPO, for example. And so what we would want is there is no systematic way to design theoretically principled surrogate functions or a unified way to analyze them. So what we want is a framework so that you can instantiate the framework and come up with like different surrogate functions. Okay, and all of them should have a guarantee. And all of them should have a guarantee for general function approximation. So we don't want to restrict ourselves to like either the tabular or the linear function approximation setting. Okay, so this is our wish list, and that is what this talk is going to be about. Okay, so interrupt me anytime if you have a question. Okay, so let's get started. So formal problem definition, I think we can breeze through this one. So infinite horizon discounted MDP, gamma is the discount factor, rho is the starting state. I think the only non-standard notation I will use is this p pi, which is the distribution over actions for a given state S. Okay? And everything else I think is standard. D pi of S is the distribution over the states, the state occupancy measure, and the state action occupancy measure is going to be referred to as mu. Okay, so this is pretty standard. And the objective is that if I'm given a set of feasible policies, so that's capital pi, I need to find a policy in the set that maximizes my j pi, which is the average, like the cumulative reward, discounted cumulative. Okay, so that's pretty standard. Okay, so that's the setting we are going to be in. So now another important thing that we need is to distinguish between what is a functional representation of a policy versus its parameterization. And this is kind of key. So the functional representation specifies a policy's sufficient statistics. So for example, you can represent a policy by its state occupancy measure, or you can represent a policy by saying what is the conditional distribution over the actions for every state. So you can say, you can completely specify a policy if you give me p pi of a given S for every A. Okay. Or the other way, so this I'm going to refer to as the direct functional representation. And then there is an alternative one, which is the softmax one. So in this, we know p pi of AS, use the softmax transformation and represent it by the logics. So if I tell you the logics for every state and action, again, you have completely specified the policy. Okay, so that is what I mean. This is a way to represent the policy. Okay, and this we are going to decouple with what it means to parameterize. So a policy parameterization is a way that we realize these representations. Okay, and this dictates what is the set of feasible policies. Okay, so you have like a neural network. You can represent all of these things using a neural network. So these class of policies that can be represented by this neural network constitute this set pi, capital Pi. Okay, so the tabular parameterization is this tabular setting in which we have a parameter for every state and action. Okay, so existing results are for this tabular parameterization. They prove like very strong guarantees on policy gradient methods, for example. Or you could say, I want a linear parameterization. So I can say all my logics, linear function of theta and these features for every state and action. Okay? Or you can say each one of these logics come from a neural network. Okay, so it can be anything you want it to be. So throughout this talk, yes?
Sorry, stupid question. What's the difference between P pi and the policy?
Oh, so pi is going to be the representation. So it could either be P pi or the logits. So I'm just going to use it as like a general.
Not just the policy, just different. Okay.
Yeah, and P pi is like the specific, like the distribution. Yeah. Okay, so and throughout this talk, I'm not going to bother about what is the policy parameterization. The thing that is going to be important is how we represent the policy. So you can throw in a neural network, and actually, I'll just make this implicit in the notation. So I'm just going to like make it implicit, and I'll show that on the next slide. Okay, so importantly, the functional representation is independent of its parameterization. So yes.
So is this the same as saying that the mapping from whatever parameter space to the conditional distribution, that is a composition of two functions? Okay.
Yes. So that's what I'm saying. So that's what he's saying. So this is the composition. So it's J of pi of theta. And pi of theta, the model is in this map. And what standard policy gradient methods do is they directly get to J pi of theta and optimize with respect to theta. Okay, so that is what is the standard approach. So now what we are going to do is try to optimize with respect to pi. So instead of going through this composition completely, we're going to split it. Okay, and that we will see will give rise to like these surrogate functions. So that's like the main idea. Questions? Yep.
By surrogate function, you mean like an extra critic model?
That will be towards the end. But for now, in the beginning, only policy optimization. So like PPO has like a surrogate function in every iteration that it maximizes with respect to like theta or like TRPO. So those are the surrogate functions I'm referring. Okay, let's move on. Okay, so this is our framework. So like I said, the idea is to optimize J with respect to pi directly. And for the parameterization, I'm going to project the resulting policy onto the set capital pi, and that depends on the parameterization. So I'm like splitting the two things. Okay, so and to answer that question, small pi is the general functional representation, and if I realize it by some model, it's implicit in this pi of theta notation. Okay, so it could be a neural network, it could be a linear function approximator, whatever you want it. Okay, so and we are going to do mirror descent. So just some mirror descent stuff. So phi, capital phi, is the mirror map. It's a strictly convex differentiable function, and it tells you what is a measure of distance between these policies, or the representation of these policies, pi and pi prime. Okay, and this is the form. And what we're going to do is mirror descent. Okay, so what is mirror descent? So you map. This is the primal space, the dual space. This is the mirror map. You take your iterate, map it to the dual space, do a gradient ascent step here, and then map it back, and that's the first equation on the left. And then this need not be in the set of feasible policies, so we do a projection. And we do a projection, and the metric we use is this Bregman divergence. Okay, so this is like called the Bregman projection. Okay, is this all pretty standard? Yes. Yes. So the key is that the parameterization only is in here. Everything else is in the representation. Okay, so you can rewrite this, and this is the form we are going to go with, is that you take the max over pi. This is the gradient, so you move in the direction of the gradient, and you want to stay close to the previous policy. Okay, and how close? How do you measure closeness? You measure closeness according to this divergence. Okay, so if you choose a Euclidean mirror map, this becomes exactly gradient descent. Okay, so that's the backward compatibility. Okay. Questions? Yep.
I'm concerned that this set of policies that we can represent might not be convex.
Yes, yes, definitely. Yeah, yeah. Next slide.
Yeah. Suppose.
Okay. So the complexity of, okay, so I think I am having Lynn's problem.
I have no problem.
No, the
Yeah,
same
I'm
problem.
Sharing a problem.
Have a solution.
Yes, so phi could be, say, negative entropy. So if your representation involves distributions, then you should use a negative entropy mirror map so that the divergence function, the Bregman divergence, is like the KL divergence. Oh, on the policy, on P pi of S. So the state action distributions. Okay. So we are going to have a minor problem. Oh, I actually lost connection to the Wi-Fi.
Oh,
Yes.
guest or?
Yeah, I was on guest.
Should I just hotspot it?
Oh yeah.
Or
that's
you
what I
can
did.
log into your, that's easier for you.
Yeah, even I
No,
can
I have a
just
complex
hotspot.
password rather than to look up.
Oh, I can hotspot it. Mine.
Okay.
Yeah,
Let's see.
You know, okay. Actually, I'll have to connect to the network, not the guest one.
Mine is I'm there.
That's not it. It's it.
Okay. Okay, and we are back. So the complexity of projection depends on the parameterization. So tabular, everything is fine. Linear, it's restricted, but it's convex. And like Chava was saying, if you use a neural network, capital pi is going to be non-convex and making the projection ill-defined. Okay, so there's a potential problem there. Okay. So what we are going to do is we're going to say, because capital pi consists of policies that are realizable by some model, instead of solving this projection step, I am just going to look for the theta such that when I parameterize this policy, it's the closest to the projection in terms of the Bregman divergence. Okay, so we haven't done anything. We have just we now have a crazy non-convex, non-concave problem. So it does not solve our problem yet. Yes.
So this Bregman divergence assumes the pi t plus a half is also a policy.
It does not need to be realizable by the model.
I mean, so, but it may not be a policy at all. Like
Oh yeah, it can be anything you
It can
want.
be
Yeah,
anything.
yeah. Okay, so at least by this, we ensure that pi t plus 1 is in the class of policies. Now, how to solve this, we do not know. Okay, this is like a non-convex problem. So what we're going to do, we're just going to write this explicitly, and this is, so pi t plus 1 is pi of theta t plus 1, and I just put in pi t plus half and just solve it. So I get theta t plus 1 is the solution to this. Okay, and this I will refer to as our surrogate function. So again, nothing has happened. I have just moved the non-convexity into this function. Okay, so this is non-concave. I'm going to do gradient descent. Okay, so this is non-concave in general, and we are going to optimize it using gradient descent.
and the second term is due to the mirror. That is
Yes, so this is the divergence between the two policies. This is J with respect to pi,
Yeah.
right? So this is the functional gradient.
function.
So there is no gradient with respect to theta over here, and all of these are parameter in terms of. So the model is here. So whenever you see pi of theta, imagine like a linear or like a neural network. Yeah. So this is where we are.
Is that computable?
No, we are just going to try and maximize it using one step of or 5 steps of gradient descent. So m steps of gradient descent. Okay? So the algorithm is officially this. So compute the gradient of j with respect to pi, form the surrogate function that we saw on the last slide, and try to optimize this using gradient descent.
Is that gradient of pi computable?
Yes, so that I will instantiate in like the softmax case and the direct case. It turns out that it's like Q functions or the advantage. It depends on these things. So these now correspond to off-policy actor updates. So you can update the parameters of the policy, which is omega, without interacting with the environment. So the environment interaction is only for the first line to compute the gradient of j with respect to pi. Okay, so we have like split the two things. Okay, so inside there is still some non-concave function, but that's fine. Okay. Okay, so this is the framework. Any questions?
So the gradient of j with respect to pi is the high dimensional,
Exactly. Yeah, and we're never going to like actually form it.
but we'll get estimates of it.
Exactly. Yeah. Other questions? So, yeah, should I go on? Okay. So let's try to see what we can prove, because this is the theory workshop. So let's see what we do. So remember, so the first line is I just rewrote the surrogate, and the least thing we would want is that j pi t plus 1 is greater than j pi t. So at every iteration, I want to ensure that at least the policy is improved. Okay. So that is the first thing we want, is monotonic policy improvement. So for this, we need these two conditions suffice, is that you improve the surrogate by gradient ascent. And then the other thing that we need is that we want the surrogate to be a global lower bound on j pi of theta. Okay, so we want the second thing to be true for all theta. Okay, and if I have these two, my claim is that I can prove that j pi t plus 1 is going to be bigger than j pi t. Okay, so I'm always improving the policy. Okay, so to do this, to see this, this is the sequence of inequalities. So j pi t plus 1 is j of pi theta t plus 1, right? This is a global upper bound, surrogate is a global lower bound. So this is true because of the second equation, and I get LT theta t plus 1. I improve the surrogate by using gradient ascent in the inner loop. And this, if you look at that inequality, the surrogate, it is tight at pi t. So if you put theta equal to theta t, you get j pi theta t, and you get it. So if 1 and 2 are satisfied, you are always improving the policy. Okay, and this does not depend on the policy parameterization. You can have it to as complicated as you want it, and this will always ensure that you get convergence to a stationary point. Okay, so that's like the basic thing that we should check. Okay, and the convergence you can prove is like at a 1 over t rate. Okay, so moral of the story, like even if you do many steps of off-policy updates, regardless of the policy parameterization, you can still always get convergence to the stationary point if 1 and 2 these conditions are satisfied. Okay, any questions? Yeah.
The monotonic improvement is in expectation.
There is no randomness at the moment.
Oh, okay.
Yeah, so the sampling is going to be later in the talk. Yeah. So at this moment, assume that the gradient of j with respect to pi is exact.
Okay.
Yeah, I'll put in the sampling later. Yep.
So the surrogate being a global lower bound on J. Can you expand on that?
Yes. Next. Yeah, I'll tell you how we do it. So the first one is easy, right? Because the first one is that you should only improve like a parametric function, and if you set the step size for the gradient ascent step according to the smoothness of the surrogate, for any m is the number of inner loops you do, this guarantees that one is satisfied. Okay, this is the easy part. The trickier part is the one Chaba asked, is how should we set eta so that LT of theta is always a lower bound, and this you should set eta according to the relative smoothness of j pi with respect to the divergence. Okay, so one of them is the smoothness, is this like parametric smoothness, and this is like the functional smoothness, right? This, the way we do it is we say that there exists an eta such that j plus 1 over eta times phi is convex in phi. If this is true, then that is satisfied. Then it's a global lower bound. And for the representations that when I'm going to instantiate this, I'm going to tell you what eta should you use so that you satisfy this condition.
Seems like a stretch for neural networks. So
Oh, this one, but Chava, this does not depend on the parameterization. This is only in the functional space.
yeah,
The parameterization part is here. You can do army or line search here because this is a deterministic problem.
there's the nonlinearity of chain I, which is you're finding there.
Yes,
Ah.
yes, and it's like as if you're in the tabular setting.
Right, right.
And then we use Jincheng, your like
I see.
you can get smoothness, you can everything is fine.
Should you think of the choice of phi as just being determined by the functional form?
Yes, yes. So when I instantiate this, this will become clear. Other questions? Okay, moving on. Okay, so let's instantiate it. So like he asked, so if we choose the policy to be represented by these distributions, I'm going to select, we need to choose a d phi. So I'm going to choose the d phi that decomposes across states, so that it's like d pi of s, and then some other Bregman divergence on the distributions. Okay, and for this, I'm going to use negative entropy. Okay. So just let me write this. Yes. So the first part, so to form the surrogate, we need the gradient of j with respect to pi, and that's this. This is just the policy gradient theorem. And then we need to instantiate what is this divergence. Okay. And I'm going to do this by saying it is negative entropy, and I'm going to get the KL divergence.
So regarding the choice of the phi, so the mirror descent results, didn't you need the d phi to be a Bregman divergence with respect to function phi?
Yes.
Some function.
Yeah, yeah.
phi,
So
and then-
convex linear Bregman divergence is a divergence.
Okay.
Like because d pi of s is like positive, right?
So are you saying that the capital phi? What's the capital phi here?
Oh, so that
corresponds to a little phi.
yeah. So it's like there is an additive. There's some sum inside the capital phi, which becomes a sum in the d phi.
So that's the
It's like-
same as entropy, but on the occupancy distribution.
Yes. Yeah. So just like everything decomposes state-wise. So this is the surrogate we get. So now the algorithm is just going to try and in every iteration, it's going to try and optimize this. Okay, so it has a q pi t here. That this is the thing that needs to be estimated by sampling. And there is an important sampling ratio here, and there's a KL divergence here, which is like p pi t. Okay. So
This is direct parameterization.
Yes, this is the one where we used p pi of s over actions for every state. So that's the way we are representing the policy. Okay, and to address Chava's question, so in this case, you can set eta to be this, and then this ensures that it is a global lower bound. This is the smoothness of j pi with respect to pi. This is like from like the paper by like Shah, Malik, and Jason. So this is one way to instantiate it. So let's compare against things. So if you use a tabular parameterization, so if you forget, so pi theta is, so if p pi of a given s is exactly p pi of a given s, so there is a parameter per state and action, then this becomes similar to this uniform TRPO or this MD MPI by like Matthew Weiss and these people. If you optimize the surrogate exactly, you recover softmax or like reinforce. If you use a negative entropy mirror map, you recover natural policy gradient. Okay. So it's like if you are in the tabular parameterization, if you solve the surrogate exactly, you recover all these things because you're projecting exactly, right? So that's kind of intuitive. And if you the resulting update is the same as this NDPO thing, but we are going to set step sizes so that we get monotonic. Okay, so there are two downsides with this representation. One of them is that it involves the importance sampling ratio, and that could be potentially large. And the other one is that it involves the reverse scale divergence. So if you look at the direction of the divergence, it's pi pi t. So that's the reverse scale, and that's mode seeking. So it's going to try and put all its mass on one of the modes. And that is what we don't want. We want to spread the mass to encourage exploration. Okay? So this is so these are the two things that we want to address. And the next instantiation will address both of these. Okay. So before that, any questions?
So the benefit of this approach is to have all those.
Yeah, so we get like these surrogate functions, and any number of steps you do to optimize these surrogate functions ensures that you're always improving the policy. So if you take TRPO and optimize that surrogate function, there is no guarantee that you will improve the policy with like general function approximation. It's only in the tabular setting. Okay, so the benefit of splitting it into the functional and parametric part is that you can treat both of these things like separately. Okay, so let's do the other one. So in this, the policy is represented by the logics. So Z pi of SA, such that this distribution is proportional to this exponential. So this is like the softmax thing. And in this case, again, we need to choose a divergence. But at least the gradient of J pi with respect to Z pi is D pi of S, the advantage multiplied by the P. Okay, this is again policy gradient theorem. Okay, so the surrogate becomes something like this. And this is the thing we want to instantiate now. Now we have to choose a Bregman divert, a mirror map to make this kind of simple. So the one we choose is log sum x. So log sum x is a good choice because it is the Fenchel conjugate of negative entropy. So it's basically you can go back and forth between the two representations. So in this case, the surrogate becomes this. And again, we prove that if the step size is less than 1 minus gamma, then it is a global Dover. So again, everything the same, but there are going to be certain advantages to this, and I'll explain that on the next slide. Any questions before that? Yes.
Is there like a principle of choosing view map?
We chose because they were like Fenchel conjugates. You can choose like the Euclidean one in which you'll get back like softmax policy gradient, but I don't know if there is like a better mirror map. Yeah, that we haven't thought of yet. Okay. Okay, so in this case, the surrogate, you can rewrite it like this. So the reason I rewrote it in this way is that you get the log of the importance sampling ratio instead of the importance sampling ratio, and you get the KL in the opposite direction. Okay, so that's the advantage. Okay, so, and the surrogate involves the forward KL, making it more covering. Okay, and now you should compare this surrogate to the surrogate for TRPO. So TRPO is very similar, but we came to this in this nice principled way. They have importance sampling ratio. We have the log of it. So that's one thing. And they enforce the proximity between the policies via constraint, and we have a regularization. Okay? They don't know how to set delta. We know how to set eta. So that's like the main comparison. Okay. So any questions? Okay, so that's part one. Okay, so we have like this framework which ensures monotonic policy improvement. And recently we use this framework to lift existing theoretical guarantees. So because all these guarantees for policy gradients are like in the tabular setting, and you can immediately lift them to the linear function approximation setting, but like basically for free, because we do the splitting. And then we have like some experiments, which I'm not going to go into, which show that yeah, it's competitive against like these methods. And then if you take this method and do a bit of clipping hacks, you can get a variant of PPO, which is actually better. So this is where we are at this point.
Yeah. So you showed that it's monotonic improving. Does it converge up?
So you can show it will converge to the optimal policy for linear function approximation. In general, you can't, of course. So like you can get convergence to the optimal policy if the surrogate that we had is smooth and satisfies a PL condition. So if you're like in the linear setting, then both of these are immediately satisfied and you can get a guarantee. Some people say there are like neural networks that satisfy some sort of PL condition. If you satisfy the PL condition, this will converge to the optimal
Do
policy.
you need this mismatch ratio, like in their paper? Is it?
Oh yes, that will still show up. Yeah, yeah. So it's basically like we took Sham and like Jin Cheng's results and basically did like 2 lines of proof over it, and basically yeah. So all the problems with that are still there, but the benefit is that you can get function approximation.
Right, convergence if you have this good.
Yeah, if it's bounded. Yeah, this concentrability thing is bounded. Yeah.
From the doing the mirror descent or the state action space, you get a log SA. You're, like imagine things are nice linear function approximation.
A log essay for what?
Because of the diameter of the space of occupancy.
Oh
vectors.
yes. Yeah, I think so. I think you can avoid it in like with Lin Xiao's proof. And that's the one we modified. I think in the original like Sham Alek paper, you got it, but I think he had a way to avoid it. And that's the one we modified. Yes.
So you just approach your the assumption that you can get the pure function exactly.
For up to now, yes. Next slide, I'm going to relax it. Okay, so let's relax it. So this is the part that we recently did, and I can, depending on time, we can go a little fast if you want. Okay, so we rely on getting the true gradient, which involves either like getting the exact Q pi or the advantage, and this is not like typically possible and makes it the whole thing impractical. Okay, so now what we want. So the idea is that we had like this lower bound on J that we were optimizing. So that we want to generalize to handle inexact gradients. So this is one of the propositions we prove in this paper, is that if you have any gradient estimator G hat T at an iteration T, C is some parameter, and eta again is the same, then J pi minus J pi T is greater than the sum of these two terms. The green term is the actor term, and the blue term is the critic term. Okay, so phi star is the French conjugate. This does not depend on pi. This only depends on your current policy and how bad is your gradient approximation. So if G hat is very good, it is equal to J pi D, and this term is going to vanish, and we're going to back in the same place. Here we have G hat. So if we want to optimize this surrogate, we don't need the knowledge of the gradient of J with respect to pi. This gradient estimator is very fine. Okay, so this is true for any gradient estimator and any C. Okay, so the C is a trade-off between the two terms. So if your gradient estimator is very small, is very good, you can make C very large, and basically this term will go away. If your estimation is very bad, then you have to make C very small, and then basically what the algorithm says that you should not move too much. So it's like a trade-off between which is dictated by how good your gradient estimator is. Okay? And the gradient estimator in this case is basically how well you estimate the Q function or the advantage, and that's why I'm going to refer to the blue term as like the critic error. Okay? So that's the policy. The green term is the policy part. The blue term is the critic part. Okay? So the nice part of this is that now, because of this, we have a joint objective for training the actor and the critic, and both of them are going to like cooperate to try and minimize the same lower bound. And the lower bound is directly on J pi minus J pi T. So if you make this small, you're going to improve the policy. Okay. So this is in contrast to like standard actor critic ways that you minimize like the TD error, which need not be connected to the actual policy, like the value function that you actually want to optimize. So that's like one benefit. And this is in the literature, this is called like decision aware RL. Okay, so because you're optimizing the critic, because you're like aware of the decision Yeah, I don't know. That is what people call it.
Just do the right thing.
Yes, basically just do the right thing. Yeah, and the other way of coupling the actor and the critic is through the linear programming formulation that Matthew described. So this is like an alternative. Okay, so this is good. So now we have an actor critic way. Again, I'm just going to make the critic parameterization implicit. So omega is the critic parameter. So you do like TD, get some like samples with bootstrapping, try to minimize this function instead of the squared loss, do the actor update in this exactly the same way. So you have like critic updates and again off policy updates. So this is the whole algorithm. Okay. Any questions?
Where you got this? Is this one like directly interact with the environment? Or
Oh, that's the first line. Yes, the first line of the for loop is that you get some samples from like S prime pair, update your critic, get G hat, use G hat to update your actor.
one sample to get
One sample is fine. Yeah,
the infinite horizon.
infinite. Yeah, so in the theory I will show on the next slide, we just kind of abstracted this away. So it's like you have some error in your gradient. You can do one sample, you can do bootstrapping, whatever, or you can do Monte Carlo rollouts. All of this is a source of error, and we are just going to treat all these sources of error in like a similar way. So we kind of abstracted that out. If you dig into it, I think you can prove something better. Okay, so let's, what do we prove? Oh, sorry. Yes, no. Yes. Yeah, that's the other tricky part. Okay, so what can we prove? So this is one thing we proved. So for any policy and critic parameterization, again, it can be neural networks, there always exists a theta, like a way to update the surrogate, and a setting of the C, this hyperparameter, that makes the RHS of that inequality that we had positive. Basically, if you make it positive, it implies that j pi t plus 1 is greater than j pi t. If and only if the critic error is like small enough. So basically, this is the condition that says if your critic error is too large, no one can guarantee policy improvement. But if it is small enough, we can always find a theta and a C that can guarantee monotonic policy. Okay, so it's like a necessary and sufficient condition. Okay, so how does this look like? So it's kind of complicated. That's why I didn't put it on the slides. But if you're in the tabular setting, tabular policy parameterization with a Euclidean mirror map, the condition comes out to be this. So that's like saying the relative error in your gradient is smaller than 1. Okay, so if your like signal to noise ratio is larger than 1, you can improve the policy, else you can't. If you use a general policy, general mirror map, over here, instead of the 2 norm, it becomes the norm induced in the Hessian of the mirror map. So it becomes like an induced norm. Questions? So this is kind of surprising in the sense that it's true for any policy parameterization. Okay, any questions? Yeah, I have the full form in the backup slides if you want to stare at it later.
Well,
Yeah.
I was just wondering whether you should have an expectation of G hat in the measurement of the errors, treat the noise in G hat separately. from-
Yes, yeah.
All the errors can apply.
Yeah. So yeah, so when we wrote this part of the paper, in the paper I say that you can split this into like the bias and the variance. The variance is because of like the sampling, the bias is because of the function approximation. Yeah, you can split it. Because the d phi star thing, like this thing is convex in G hat. So you can just do that Jensen and just split it. Okay, so final thing. So if the critic error is not small enough, then at least you can guarantee convergence to the stationary. you can't improve the policy always, but at least you can get convergence to the neighborhood of a stationary point, and the neighborhood depends on error and the number of actor updates you do. And this is under an additional assumption that the surrogate is smooth and satisfies like this VL condition. So yeah, so that's the, yeah, basically this one is like a mirror descent proof.
So will that surrogate satisfy the PL?
For linear function approximation, yes. In general, I don't know. Yeah, I think we ensured that linear function approximation satisfies like all our things. Yeah. Okay. So, oh, and the last slide, I guess, is that if you instantiate it, you get the act. So the green is the actor surrogate, exactly what we had previously, and the blue thing now is the critic error. Okay, so this says that you should measure the critic error according to this weird function rather than the squared norm. Okay, so it is asymmetric, and it treats the overestimation and the underestimation separately, like differently. So that's why it is kind of important if you have like limited function capacity for your critic, you're better off spending it to minimize this function and not caring about the parts that you like that overestimated, for example. Okay, so this is different from this, which treats everything in the same way and tries to minimize like the squared norm. Okay. Okay, so this is the decision-aware critic loss. It is important if you use limited capacity. And then we have like kind of some cute bandit problems, which show that if you have like a two-arm bandit with deterministic rewards, if you use a linear parameterization for the critic with like one parameter, then if you minimize this, you will not converge to the optimal arm. But if you minimize this as the critic, you will converge to the optimal arm. Because if you minimize this decision-aware loss, it is basically spending the function approximation capacity on the correct action to minimize it. And that is what leads to convergence. Okay, so this basically was an example to show that if you use this decision-aware critic loss, it is kind of important because with this, the bias is 0. But if you use the squared loss, the algorithm gets confused because it spreads its capacity on both the things, even the unimportant things, and that's why it can't converge to the true policy or the true optimal arm in this case. And then we have like some similar results for the softmax thing. Okay, and I'm done. Okay, so what we want to do next is prove rates of convergence to the optimal policy for the actor critic algorithm. And then do some deep RL experiments because at the moment I'm not like completely sold on the experimental part. Okay, that's it.
Questions? It was a pretty packed talk. There's an archive paper.
Yes. Yeah.
And
There
then,
was also a question back here.
okay.
Just curious, besides the entropy function, what other functions you know at the point? If that's complexity.
Oh, so for the softmax one, we used loxamax. So it depends on the representation. We used entropy because negative entropy because it was a distribution. You can use like other forms of entropy, like Salas entropy. All these other variants should work. But I don't know why we would want to do those. So like how to choose a good mirror map at the moment is like unclear.
I did have a question too, for the linear function approximation part. Was there something about linearizability here or like
In this one?
like when you said that you made sure that it works with linear function approximation, what do you exactly mean by?
Oh, that it satisfies all the assumptions. But you get only convergence to a neighborhood of the stationary point.
Is
So
there misspecification?
yeah, then it will.
Misspecification?
If it is misspecified, it leads to an additional bias.
Features are used to represent action value functions or
Yes.
which
Yeah, that is the one we did, but it does not matter. Like the form of it does not matter.
okay. I just want to know one result.
Okay, so in our experiments, we parameterize the state action Q functions. Yeah.
And is the implicit assumption that all action value functions are representative of the features?
You get a bias.
Or the iteration satisfy this kind of theory.
Yeah. I was just saying all the assumptions that we have are satisfied by the linear function approximation.
We can take it offline.
Yeah.
I think I don't understand it. Okay. Right. Let's send Sharon again.